All right, so in this video, we're going to take a look at the Tonescale functionality of OpenDRT in a bit more detail. And we're just in the same nuke graph as we had before. So we have our read nodes up here and some stuff for visualizing some test patterns and OpenDRT. We have our viewer set up to Rec 1886, and OpenDRT is set up to output display linear. So the EOTF is linear and clamp is off, just so we can visualize the linear data coming out of the picture formation. So we have our scene linear input, and we have our picture formation as represented by OpenDRT with the default preset. And then we have some other stuff in here. So what we're going to do is try to visualize the kind of the neutral axis or the gray axis so that we can have a look at the behavior of these various parameters in the Tonescale tab. So to do this, I have a little setup here where I'm taking a linear gradient from 0 to 1. I'm cropping out just the bottom 10 pixels and merging that over so we have kind of a representation of the neutral axis overlaid over the image. And then down here I have a plot, which basically, if we turn off OpenDRT, we can see that it's plotting scanline number 5, so right in the middle of our little ramp there. And you can see it's a linear gradient. So if we turn on OpenDRT, you can see that the values are being compressed down by the Tonescale. And this isn't a very good way of visualizing things because we're kind of not representing any input pixel value in the scene linear domain above 1, because this is a ramp from 0 to 1. So we could do something like multiply up the max value so that we're visualizing between like 0 and 30. But this isn't really helpful because we're not seeing any of that detail in the midtones and shadows, which our eyes are super sensitive to. So what we're going to do instead is turn on a log to lin conversion. So this is a kind of like an exponential transform from negative 0.006 up to 256 or so. And that places middle gray, roughly over here, so we can kind of have a better idea what's going on. And if we look at the result, we can see kind of the S-shaped view transform that people talk about when visualizing this kind of thing on a log ranging axis. And this is kind of like a semi-log plot. So the x-axis is a exponentially ranging or exponentially scaled graph, and then the y is kind of like a linear, like display linear, if we can think about it that way, pixel range. So yeah, at the bottom where y equals 0, the pixel value is 0, and where y equals 1 on the image, the pixel value is 1. And this is cool, but we're not really seeing as much detail into the shadows as could be useful. So I have this other optional setup here to bias the plot by a 1/2.4 power function or a 2.4 gamma. And that lets us see a bit more clearly what's happening in the shadows and midtones. So throughout this, I'll turn this on or off depending on what we're looking at. Cool. So that is the setup. And okay, so we'll start talking about the Tonescale options in OpenDRT. And we're going to skip the HDR parameters until the end because it's a bit more complex. And first we'll talk about the kind of basic Tonescale parameters, and then we'll chat about the the kind of look modules in the Tonescale function, which is the contrast high and contrast low. So first we'll look at the gray luminance. And basically, if we adjust the gray luminance up or down, you can see that the curve is kind of shifting left or right, and the overall exposure of the image is changing. And actually, this is exactly matching an exposure if we turn the offset to 0. Which I'll just kind of reset this for the moment. So yeah, if we do a multiply upstream in the scene linear domain and we multiply up or down, you can see that the result is quite similar to the gray luminance adjustment. And yeah, so that's the gray luminance. And basically, this is a measure in nits rather than in kind of an absolute display linear value output. So what's being output is the number of nits of middle gray, or a 0.18 input, relative to the peak luminance that you have set. So if we enter 18 here, this will actually output a scene linear value of 0.18 out to a scene linear value of 0.18. And if we change this down to 10, it'll be around 0.1. Yeah, so that's kind of the thinking there. Most camera manufacturer imaging pipeline picture formation approaches use around 11.1 nits or 0.11 output. And the reason for that is to be compatible with the Rec. 709 camera OETF. We stick with that standard for most of the Tonescale presets, but at the end of the day, this is a creative decision. Cool, so that's the gray luminance. And yeah, contrast is about what you would expect. So if we reduce the contrast or increase it, you can see that the pivot of, well, this curve is basically pivoting at 0.18. So in this control, that has an intersection constraint so that middle gray doesn't change. And we can prove that if we look at our output here and adjust the contrast. This isn't changing. Cool. So yeah, contrast is important to set kind of before you go into the purity, because as you can see, when we adjust the contrast here, the reaction of the saturation isn't really as you would expect doing this with a per channel type transform. So we're doing this with more of a chromaticity RGB ratio preserving approach so that the color isn't affected by this curve. Although the color is being affected through OpenDRT because the shape of this curve determines the purity compression behavior. But yeah, anyways, so good to keep that in mind. The shoulder clip is basically the intersection constraint at the top end, and we prioritize a exact intersection constraint at middle gray at 0.18 in the Tonescale math. And it's not really possible to do an exact intersection constraint at both the peak luminance and at middle gray without much more complicated math. So, and the intersection constraint at the peak is much less important overall because it's kind of buried in the few code values at the top there. So basically what we did instead is we have a kind of abstract slider range from 0 to 1, where 0 represents a scene referred intersection constraint at the top end of about 16, and at 1 it's like 1024, so very, very high. And yeah, so this just strips by default at 0.5, which is about 128, I believe, or maybe 256, I forget. And yeah, so that's what that does. Okay, next up we'll talk about the toe. So basically with toe at 0, you can see that because of our 1/2.4 power function down here at the end, we're seeing kind of a sudden transition from 0 up. And obviously this is not in the display linear output because that's something we're adding. But it is visually important to have a smooth transition into the minimum luminance coming out of the transform. So this gives you the ability to add a little bit of compression just down there at the toe, at the very, very deep shadows. So it's important to have this, in my humble opinion, in order to get kind of a robust, smooth transform that's not going to give you artifacts, especially if you're grading in log upstream with a log curve that has a linear toe. Can be a very, very small value, like even 0.001 can be totally fine if you want to map scene linear 0 to display linear 0. Cool, so we'll just leave it at that for now. And then lastly, the offset is, as you would expect, just a add prior to the Tonescale system. So with an offset of 0, scene linear 0 is mapped to display linear 0. And if we boost this up, we can see that the output is being increased. It's not an exact match because it's an offset prior to the Tonescale system. It's not important for it to be an exact match. So yeah, if we boost the value up, we can see that the blacks are being lifted a little bit. So just another creative control, although I will mention that it is quite common for camera imaging pipelines to have negative pixels and shadow grain. So if we choose an image here with some deep shadows and look at the output in the scene referred domain, we can see that there's negative pixels here. And the reason for that is to place that average of shadow grain at 0 rather than the minimum value of shadow grain. And it's debatable if this is a good thing or a bad thing, but the reality is that it's very common for camera raw images to come to us like this. So if we add a bit of offset, like say a small value like 0.005, looking at our display linear output again, you can see that it's lifting up the shadows just a little bit, and I'm gammaed up here, so it's a big change, but if we go back down, we can see it's kind of just shifting the minimum value of the tone scale curve left, which is mapping to a positive value. And you can see that when we adjust this, the middle gray is constrained to the output through this transform, so middle gray isn't changing. And as a byproduct of that, if we do a very strong positive offset, contrast at the top end is being reduced slightly, but that's all well and good. So there's a few ways to do this. You could do no offset at all if you're doing a positive offset for shadow grain earlier in your pipeline. You could do a very small positive offset. You could do an offset for kind of aesthetic reasons. Lifted blacks is quite in vogue at the moment in terms of grading looks. There's also other approaches, like you could do a very strong offset and then also crank up the toe. And this gives you like a really nice smooth transition into shadows, which can be kind of, pleasing. So some of the tone scale presets use this approach, and this is a approach that's pretty common with camera imaging pipelines. So like the REK1S1, that old transform uses something like this, and it's quite well regarded aesthetically. Various options. Cool, so just reset this to, ACES1, sorry. So next we'll talk about the contrast high. So I'll just reset this. Okay, so contrast high is a adjustment that basically lets you adjust the contrast of the highlights, and please put highlights in scare quotes. So if we boost this up a bit, you can see that it's just adjusting the slope at the top end of the curve. And conversely, if we go down, it's reducing the slope at the top end of the curve. So if you want your highlights to pop a bit more, or you want to have more of a smooth roll off into highlights, you can achieve that with this. And this is number of stops to expose up or down. And then the pivot is basically the amount of stops above middle gray to start the adjustment. So at 0, it's going to start pivoting at middle gray, which is down here. And if we boost this up a bit, you can see that the adjustment is starting a bit higher. So if this is at 1, it's 1 stop above middle gray. Pretty straightforward. And then the strength is basically how quickly to begin the adjustment above. So if strength is at 0, this doesn't do anything. And if strength is increased, you start to get more and more of a, kind of like a more strong transition into the effect, if that makes sense. Cool. Next is the contrast low. So I'll go back to like a picture of a face. So without this adjustment, it's quite difficult to get kind of like a finished looking picture because the tone scale system doesn't have a lot of contrast at the bottom end. So we add this module in order to have some control over the kind of lower midtones and shadows contrast. This math is pretty similar to the quadratic toe compression, except that it's cubic, and there's an additional power function to control the strength. So if we boost contrast low up a bit, you can see that it's kind of increasing contrast mainly at the bottom end, and this is also constrained through middle gray. So as a byproduct, you get an increase in contrast above middle gray as well. And so this is just like how much to expose down the toe. And this is quite different than a typical power function based contrast because you're explicitly controlling the slope at 0. So you can see even if we crank this up pretty far, the slope into the minimum value is not going to 0, which is quite nice behavior. Okay, so the width is basically kind of like the strength of the adjustment here. So if we set the width quite low and we adjust this up or down, we can see we're kind of only affecting more of the like darker shadow region. And the more we boost this up, the more we start to affect midtones. So this can be used to creative effect. You can actually boost this up really high and get kind of like a interesting effect where you're increasing shadow contrast a little bit and also highlight contrast a little bit. Like we could do that and have our main contrast lower and get kind of an interesting different looking contrast. Cool. And then lastly is the contrast low per channel. So this is basically a slider that mixes between a chromaticity / RGB ratio preserving approach and a per channel approach. This is the only place in OpenDRT that actually uses a channel by channel curve. And the reason is that in the low end, it actually does quite nice things to color. So as we increase, you can see that hue contrast is being increased a little bit, which means that the stimuli is being kind of compressed towards the primaries, so red, green, and blue. And we're increasing saturation in kind of the mid-purity regions as we increase this. But this is a creative control, so if you don't want that and you want to do all of your purity stuff over here, feel free to set contrast per channel to low, but we'll keep it at 1 because it's nice looking. Cool, so I'll reset this to default high contrast, and then we'll talk a little bit about creative white. So I'll be going to this picture. So creative white is basically a setting that allows you to specify the exact color of the peak luminance. So if it's D65, then it will be a D65 output. So red equals green equals blue. And that's equal code values in Rec 1886, which has a D65 white point. But if we drop this down, we can actually change the peak white point to be warmer. So all the way down to D50 if we wanted. And then we have the creative white range, which basically specifies how much to keep midtones and shadows unaffected. So if range is at 1, it's kind of like a multiply over the whole image. And if range is at 0, we're limiting the effect to more the upper highlight regions. And just to mention it, you could try to do this operation upstream of the picture formation. Like say we did a multiply upstream and we made our picture warmer, but you can see what's happening basically because we're doing this in the scene referred domain prior to the picture formation. We're tinting the image, yes, but at the peak, the purity compression at the top end is still compressing towards achromatic in the output color space, so D65. So if you want a tinting of the highlights that actually tints your highlights in the picture, you have to do this after the tone scale is applied in the picture formation. So that's why we have this option here, and don't leave it to the user. Yeah, so this can be kind of used in concert. Like if you wanted to do like kind of a split toning effect, you could also do a grade upstream and push your color a bit warmer and get like kind of a cheap split tone thing. It's not the best tool for the job, but you can't do this adjustment upstream, so I figured it's a good option to have in there. All right, so next we'll talk about HDR. And first I'll kind of describe what is HDR. So if we have some image data, like say we switch over to our test images here, and we plot this in 3D using our little RGB cube setup and a position to points, we can kind of see that this is our display referred gamut cube. So in each red, green, and blue axis, there's a 0 to 1 range, and we can't represent values above that range, right? So when we render this out to an integer output, the clamp is going to happen. So everything is kind of forced to be within this box. So the difference between SDR and HDR essentially boils down to kind of the meaning of the peak, which could be interpreted as the size of the color volume. So if we turn on a second RGB cube here, and we basically boost up the size of this thing, we can see that, it's basically making a bigger color volume. So this is 10 times bigger. So if this tiny cube down here is Rec 1886 with 100 nit peak luminance, then this bigger cube is a hypothetical HDR display that has 1000 nit peak luminance, like an LG OLED TV or something like that. So basically, in super simple terms, HDR allows us to have more creative options for our picture formation because we can choose to make our highlights brighter while keeping midtones similar, or we can choose to make our overall picture brighter. And this gives us not only more range along the neutral axis, but also more range along the RGB kind of color axes. That's a super simple explanation and completely bypassing all of the complexities of the display encoding, inverse EOTF, and all of that. But for this purpose, I don't think we need to go into that. Okay, so I have another setup over here. I'll switch back to a picture. Maybe a fire. So for this visualization, I'm gonna go to another setup where basically I have another OpenDRT, and this one is set up to output kind of the same. So we have the default preset, and basically what we're doing is we're outputting SDR, 100 nit peak luminance, and then normalizing it so that 100 nit peak luminance is at 1/6 of the display range. So effectively what that gives us is a kind of a cheat, like a visualization of what an HDR container could look like, because obviously the screen recording is done in SDR and it's not uploaded in HDR. But if you kind of squint your eyes and pretend, you'll get the idea, I think. Okay, so if we increase our peak luminance, so say we go up from 100 nits, basically what we're doing is we're scaling up the peak luminance of the image to be 600 nits now. So yeah, peak luminance is effectively that. You're just saying, what is the peak luminance of the display device that I'm outputting to? And then keeping kind of the gray point, not fixed, but changing subtly. And to see better what's happening in the midtones and shadows, I'll turn on our Gamma 2.4 visualization. So if we do this up and down, you can see our middle gray point is, being boosted up a little bit. And if we adjust HDR Grey Boost, which as the name describes, boosts the exposure of middle gray slightly with peak luminance. If we set this to 0, we can see kind of what's happening, where if we boost the peak luminance, you can see that the contrast is being increased slightly in the shadows, which usually isn't desirable. We're not using a spline or something like that where we could explicitly pin everything, and I don't think we would want to in any case because it looks unnatural. We're using kind of a quote-unquote organic tone scale system where the math kind of behaves naturally. So HDR Grey Boost is basically the number of stops per stop of peak luminance increase to boost middle gray. So if this is set to 0.1 and we go from 100 nits to 200 nits, middle gray is going to be boosted by 1/10 of a stop. And if we go up to 400, it's going to be boosted by 2/10 of a stop. And at the end of the day, this is kind of a creative control. We choose 0.13 in the defaults because that maps middle gray to about 14 nits in a 100 nit HDR container, which is kind of what seems to be evolving as a standard in camera image formation pipelines. But at the end of the day, this is creative, so feel free to adjust this as you want. And yeah, if we keep the peak luminance fixed, we can adjust this, and it's exactly the same thing as just setting your gray luminance. Cool. And then last thing is the HDR Purity. I'll go to kind of a more colorful picture here. Let's see what we got. Maybe this one. So by default, this is 0.5 actually, I think. So basically, yeah, HDR Purity allows us to adjust the colorfulness of the highlights in HDR. So if we boost the peak luminance up, we can see that the purity compression behavior is changing, which makes sense because we're changing the shape of the curve effectively. So HDR Purity basically lets us creatively control how colorful we want the HDR picture in the highlights to be. So yeah, feel free to adjust this as needed, but there's various approaches. Like for HDR, you could kind of choose to make it look exactly like the SDR version of your picture, or you could choose to adjust certain things and make it look different. So this gives you kind of another creative control. And yeah, just to explain that in a little bit more detail, if we go back to the kind of SDR version of OpenDRT, oh yeah, and just to mention it, if the EOTF is set to something that is an SDR encoding, instead of clipping everything by just boosting the peak luminance up outside of the display container, we actually normalize it so that the middle gray is coming down instead. At the end of the day, this is the same operation, it's just a normalization. But yeah, you can kind of see from this how the slope in the shoulder is getting less aggressive as we boost the peak luminance up. And that's the reason why the purity is higher when we go to a higher peak luminance. And yeah, you could use this in a different way too. Like say you wanted to adjust the peak luminance in an SDR output, but say you wanted to maybe make a version of an SDR picture that's intended for display on a 250 nit display device, which is actually quite common amongst kind of the consumer TV realm these days. So if you boost this up, it's actually the same thing as dropping your gray luminance a little bit. So I see this kind of frequently these days, where a picture formation approach will actually map middle gray to like 6 nits or something like that instead. And that's the SDR picture. And then the HDR picture just boosts up the peak luminance a little bit more, something like that. So all kinds of creative possibilities here, and this kind of gives you control over all of the details. Cool, so I think that pretty much covers the Tonescale section of the OpenDRT transform. Yeah, have fun, and thanks for listening.